chapter 3, that is the differential equations. Second part of that we are going to see here is the solution by
सर
uh,
स्क्रीन बंद झाली.
Bandari. Just a minute. Yeah, is it on?
हा हो सर.
ओके, तुझा स्क्रीन ह्या ऑफ कर, तुझा बंद करतो काय मायक्रोफोन. ओके, अँड वेनेवर आय आस्क यू शुड स्टार्ट, किंवा कोणीतरी एखादी स्टार्ट करून सांगायचं म्हणजे वेदर इट इज कंटिन्यूड ऑर नॉट. नाउ दिस इज व्हॉट ए second important method, as I said earlier, this is called as the Frobenius series solution method. Here we are given now earlier derivations or earlier part of this chapter. We have learned this method of separation of variables. So how to separate the partial differential equations into its ordinary differential equations, that how many number of variables it does contain. This entire process has been seen there. Now based upon that, next part is that once we get this type of ordinary differential equations, there is one special method for solving this type of ordinary differential equations, and this method is called as series solution method. So this method was developed by Frobenius, a French scientist, as I said earlier, and this method carries a very vital role or importance in physics as well as in mathematics. So what is that? That is what we are going to discuss here. And remember one more thing we are interested here. Yesterday we have seen there exist certain singular points. Now the success of this method or useful of this method depends upon these singular points what we have discussed yesterday. So this series can be expanded at particular value of x0 or that the independent variable, provided there exists a singularity. That means either ordinary point is existing there or a singular point is existing there, regular singular. Then it is this method is successful or that gives a correct or good result. Otherwise, whenever there exists certain irregular singularity, then it is this particular method may not give a correct result, or that's what this is the limitation of this method. That is what we are going to say at the end of this. But we must be understood why to use this method, and as we go next, when we go for actual solving several problems like Bessel differential equation, Legendre differential equations, as well as Hermite differential equations, and at that time you will understand these equations carry very vital role in physics, and thereby we need to know method of solving all these differential equations. And in that discussion we are going to come across again certain constants. So what are constants we are defining? This constant what we said earlier in the vector atom model. So principal quantum number, orbital quantum number, etc. These quantum numbers, they are basically, as I said, they come in the separation of variables also, but here also these constants carries a lot of importance and like that. Okay, so let's begin with this small derivation. In today's discussion we are going to see this method. Then there is one first theorem. That theorem directly deals with the number of so what are the what are type of singularity existing, and based upon that what are the different types of solutions possible, what are the different solutions possible that can be calculated here, and that is called as this first theorem. So that theorem also we are going to see in wording. No proof of that we are not going to discuss. And then actual method, how to apply this method for getting a series solution of any standard differential equation. And then once we understood this, then we are going to apply this for Legendre, Hermite and Bessel differential equation. Okay, so let's write in brief as follows. The linear second order homogeneous. Now all these terminologies are known to us. Homogeneous, ODE, ordinary differential equations of common occurrence, or that almost all equations have this type of format. That is what we are writing here. Have of common occurrence are of the type. Yesterday we have written that type earlier. This is given by y double dash plus p of x into y dash plus q of x into y is equal to 0. So this is a standard or common occurrence or this type of the equations which commonly occurring. These are linear second order homogeneous ordinary differential equations, where we know that y dash is the first derivative and y double dash is the second derivative. P of x and q of x are the functions of x, and this equation is to be and we have seen how to find out its singular point, whether it's a regular singular, irregular singular or ordinary point. All these things we have seen yesterday. Okay, now the most useful method of solving these equations is called Frobenius series solution method. Is called Frobenius series solution method. This was devised by Frobenius, as I said. Okay, so this method consists of obtaining a solution in the form of power series. I don't know how many of you know what do you mean by power series. That also we are going to discuss in brief. Okay, power series in the independent variables. And certain constants. So we are going to discuss what this power series is also, how it is defined, and all these things are to be seen there. Okay, now one important aspect of that, as I said here, this is said to be first theorem, FUCHS. Okay, first theorem. And this theorem, it's a theorem in mathematics, tells you so we'll write in its word, because from the examination point of view sometimes this theorem is asked, this statement is asked, so we'll write this. This theorem states that one can obtain at least one power series solution. One can obtain at least one power series solution of linear second order homogeneous equation, provided one can obtain at least one power series solution of linear second order homogeneous differential equation, provided that the point of expansion, okay, at which points we are going to find out this series solution, that is called as point of expansion. Point of expansion is an ordinary or regular singular point, In yesterday's discussion we have seen all these things. What do you mean by ordinary point, what do you mean by regular singular point, and all that. Okay, so in short, this first theorem tells you when this Frobenius series solution method will be successful, or when it will work, and when it will not work. So this Frobenius series solution method should give you correct result or not. That will be decided by following things. So there are certain points. First statement here: if the point of expansion is an ordinary, is an ordinary point. Ordinary point. Yesterday we have seen what do you mean by ordinary point. The definition also we have seen. Then the equation y double dash plus p of x y dash plus q of x into y is equal to 0 possesses two independent solutions. This is very important word we should know. Okay, so if that point of expansion is an ordinary point of that given differential equation, then this equation possesses two independent solutions or power series solution. This is first statement. We are going to get this proved in our theory or in our examples later on. Second, number 2, if the point of expansion is a regular singular point, the point of expansion is a regular singular point, then there is at least one solution. Then there is at least one power series solution. So what happens if there is an ordinary point? Then there is no issue, and we will have at least two, or that type of differential equation possesses two independent power series solutions. Whereas if the point of expansion of the if it is found to be a regular singular point of that type of differential equation, then there is at least one power series solution is possible. And third substatement of this, if the point of expansion is an irregular singular point, point of expansion is an irregular singular point, then the same equation y double dash plus p of x into y dash plus q of x into y is equal to 0 may or may not, it's not guaranteed, may or may not possess any power series solution. Okay, so try to understand. So this is the statement of first theorem. First theorem tells you whether power series solution is possible or not, because the point of expansion is to be checked for that differential equation, whether it is a ordinary point, whether it is a regular singular point or irregular singular point. Depending upon that, there can be several different types of solutions are possible, provided if it is an ordinary point, then this type of differential equation possesses two independent power series solutions. We are going to see some problems of that. Then second is, if the point of expansion around on which we are expanding this series, then if this particular point is a regular singular point of that differential equation, then there is at least one power series solution is possible for that differential equation. And provided if the given point of expansion is an irregular singular point or essential singularity, then there is no guarantee that there will be a solution or power series solution possible for that given differential equation or not. Okay, now let's go for this method. We'll go by step. The method, the series solution method. Remember, you can use this method in C programming to write the flow chart or to write the algorithm. So such type of 8 steps are there. So what these steps are, that we will discuss. Okay, before that, let me say something about what is my power series and how this power series, what is this format, how they are being expanded and like that. Okay, so again start with this. If the differential equation is of the type, differential equation is of the type, same type what we have written earlier. This is y double dash plus p of x into y dash plus q of x into y is equal to 0. Then according to Frobenius, the solution of above equation, can be written as, in terms of the power series, in the form of power series, with constant coefficients, and now look at this power series is going to be y is equal to, okay, so this differential equation in the y, so solution will be y is equal to, so here it is summation a0 plus next constant is a1 into x minus x0 plus a2 into x minus x0 square plus a3 into x minus x0 cube dot higher order terms. This bracket gets completed, multiplied by x minus x0 that raised to k. Okay, that or in short I can write y is equal to, so look at this, it can be written as summation over n equal to 0 to infinity, this is infinite power series, and this is an times x minus x0 raised to n plus k, and here the most important condition is that a0 or the first coefficient a0 should not be equal to 0. Okay, this is the star equation, this is what called as power series. Now look at this, here this x0 is our singular point or ordinary point, so whatever point, this is what, when this is a power series, when I go for this x0 is equal to that singular point, regular point, singular point or ordinary point, then this series can be expanded. So this will have this term, first term is a0 into x0 minus x0 raised to k, second term is a1 times x in minus x0 into x minus x0 k, so it becomes x minus x0 raised to 1 plus k, third term is a2 times x minus x0 raised to k plus 2, and that's what I can write. This summation, this entire power series can be written in the compact form as given by y is equal to summation over n equal to 0 to infinity en times x minus x0 raised to n plus k. Now this is the addition n plus k, so what n I am taking, if n is equal to 0 then I will get first term, if n is equal to 1 then I will get the second term, if n is equal to 2 I will get the third term, and likewise, and this x minus x0 raised to k will be there because of this k there. So this is called as a power series. Okay, so let's simplify this further. Write one statement. In the above power series, expansion is around around a point x is equal to x0. So this expansion is around the point x is equal to x0. Now if the power series is expanded, around the point this x is equal to 0, that means actually x0 is equal to 0. if it is expanded around the point x0 is equal to 0, which is we are going to test later on whether this point is a regular singular point or a irregular singular point or it is an ordinary point. Then we get this series of this above equation, start equation gets converted. Y is equal to summation or n equal to 0 to infinity. Now this is an times x raised to x minus x0 will be 0, n plus k, and here every time write this a0 is not equal to 0. This is another start equation, okay, where coefficients, all these coefficients an, okay, coefficients are constants to be determined. Once we get this constant, we get a power series, and that can be a solution of the given differential equation, okay, that is to be determined, and k is also constant. So such a series is called as a power series. So power series is expanded or is written as y is equal to a0 times a1 plus, so a0 plus a1 times x minus x0 plus a2 times x minus x0 plus a3 times x minus x0 cube dot because infinite terms are there, and multiplied by x minus x0 raised to k. So in short compact form we write this y is equal to given by this equation, first start equation, that tells you how power series is written. And remember, if this a0 is equal to 0, then this entire thing goes, that will be simply 0, nothing will happen or nothing will be possible in this particular power series, because a0, a1, a2, a3 etc. are connected to each other. If a0 is equal to 0, then a2 is 0. If a0 and a1 is 0, then a0 is 0, then a1 will be 0. If a0 and a1 are 0, then a2 will be 0, because in this case all these coefficients are connected to each other. How? That is what we are going to discuss later on. So therefore, every time whenever we write this power series in the form, this second start form, n is equal to 0 to infinity summation over n times x raised to n plus k, definitely you have to write every time this a0 is not equal to 0. If it is equal to 0, then everything fails, nothing will be possible, no solution, and no power series solution is possible in this case. So invariably every power series must have its zeroth coefficient, or first coefficient a0 must be not equal to 0, must be non-zero. If it is 0, then everything is when there is no use of this particular method. So that is what we have to go for all these things, okay. Now let's go for actual method. We'll start here. So let's study this Frobenius method to obtain the series solution of linear homogeneous second order ordinary differential equation. Okay, so let's start this. So that is called as algorithm of Frobenius method. Frobenius method. So we can use this algorithm, as I said earlier, in the C programming too, for what are the different steps are there. So this algorithm let us give in the form of the equation is y double dash plus p of x into y dash plus q of x into y is equal to 0. This is the form of the function. Let x is equal to 0 be an ordinary point, or maybe regular singular point, it can be anything of this, ordinary point or regular singular point. Therefore, according to first theorem, we can get at least one solution. We can get at least one power series solution. Okay. So before that, we have to check the singularity of the point, whether it is regular singular or whether it is ordinary point, and that is to be checked. Okay. So there are certain steps. Step Step 1 is this. Okay, this is what my equation. Okay, I am calling this to be our equation 1. So whenever such a case is existing, there exists a point x is equal to 0. I am taking origin. That if that point is ordinary point or regular singular point, then first step you have to assume that let the solution of equation 1 is in the form that is power series form. We have tried the solution y is equal to summation over n equal to 0 to infinity. It is an times x raised to n plus k. Okay, and again a0 is not equal to 0. Call this to be equation 2. Okay, now if it is existing, if this differential equation is given, and if a point is also given at which we have to expand this particular power series or the series solution, then first we have to check the given point whether it is an ordinary point or regular singular point, and if it is there, first theorem ensures there is at least one power series solution. So let us assume the solution first. So step 1 is we are assuming solution of that differential equation is of the form power series y is equal to summation over n equal to 0 to infinity an constants multiplied by x raised to n plus k, and a0 is not equal to 0. So this is what solution I am assuming. Now we have to use the same solution for calculating these constants, and then that comes a final solution as follows. Okay, so that is what step 2. Step 2nd is differentiate above equation. Okay, differentiating above equation, we get first and second differential. Differentiating above equation we get, so first differential is y dash, so that is dy by dx or y dash. So it is again a simple series is to be expanded, so summation over n equal to 0 to infinity summation over n equal to 0 to infinity. Then now differential of x raised to n plus k, so an is constant, that will remain as it is. Differential of n plus k is, first it is n plus k will come out into x raised to n plus k minus 1, just like differential of x square, d by dx of x square is x raised to 2 minus 1. Okay, like that. So it is with x raised to, so 2 will come out here, 2 into x raised to 2 minus 1, so that is twice x, like this. So I am going to get the differential of x raised to n plus k minus k will be n plus k into x raised to n plus k minus 1. This is my first differential. Similarly, second differential or differential of this, again here summation over n equal to 0 to infinity as it is, an will be there, n plus k will be there, and then again this index will come here, so it is n plus k minus 1 into x raised to n plus k minus 2 this time. So second differential. First differential is summation over n equal to 0 to infinity an times n plus k into x raised to n plus k minus 1, and y double dash is n equal to 0 to infinity an times n plus k into n plus k minus 1 multiplied by x raised to n plus k minus 2. So that power of x goes on reducing by 1 each time. Third differential also can be calculated. Y triple dash is equal to summation over n equal to 0 to infinity an times n plus k into n plus k minus 1 into n plus k minus 2 into x raised to n plus k minus 3. So that type of several differentiations also can be calculated. Okay, now substituting this, that is y dash and y double dash in equation 1, we get, substituting this y dash and y double dash in equation we get. Now this lengthy differential equation will be very lengthy. Summation over n equal to 0 to infinity, it is an times n plus k into n plus k minus 1 into x raised to n plus k minus 2. This is my first term, plus p of x was there, into summation over n equal to 0 to infinity. This time it is an times n plus k into x raised to n plus k minus 1. This is there. and plus last term is q of x into summation over n. This is y dash, and y is this summation n equal to 0 to infinity. Now this is an times x raised to n plus k is equal to 0. This is my equation 3. Okay. So Rohan, are you looking this? Distega? Hello? Rohan Gawandi?
Yes, sir.
दिसते ना? Okay. So I am going bit slow. ये थोड़ा सा slow जाता है. This is my y I have defined. This is y dash and y double dash I have calculated, and using this y dash and y double dash in our standard differential equation, that is y double dash plus p of x into y dash plus q of x into y is equal to 0. I'll get this is equation number 3. Okay. So that was equation 1. This is equation 2, and next what I am getting this equation number 3. Now this is step 2 completed here. Step 3. Step 3. Okay. Now can you identify which is the term having lowest power of x? X is सगळ्यात power कमी असणारी term कोणती असेल? That is this term. X raised to n plus k will have highest power. X raised to n plus k minus 1 is less than that, and x raised to n plus k minus 2 is again less than that. So this is the lowest power x power term. Okay, lowest power term. So we have to concentrate over this. Now lowest power terms gives you something very interesting. So equating, this step 3 is equating coefficient of the smallest power of x, remember we are not solving problem, we are understanding the method to solve problem. That's why we have to write lot of things here. Smallest power of x in equation 3 to 0. We have to equate this to 0. We get a quadratic equation in K. Okay, we get a quadratic equation in K, and that, so whatever this equation we obtained, it has a special name. The quadratic equation so obtained. The quadratic equation so obtained is called indicial equation. INDICIAL, indicial equation. The quadratic equation so obtained is called as indicial equation. And now this plays a very vital role. Whether these solutions are identical or equal or something different, like that will be decided by these roots of that particular equation, initial equation, and therefore from the equation 3 what we have obtained above, equate the coefficient of lowest power of x equal to 0, we get a quadratic equation in K, and solving this equation we get some roots, and that roots decides lot many things. So what are these? That will be seen in the next few steps. So that is indicial equation, remember. Then step 5. Okay, once we got this indicial equation, then we have to go further. After solving indicial equation, following cases arises. Now what are these cases? Case 1. First case is the roots are distinct. DISTINCT. That means they are separate from each other, distinct, and do not differ by real integer. By a real integer. This is one possibility. Second possibility, after obtaining the roots of that initial equation, is that the roots are unequal. Okay, here it is distinct and unequal, two different words. Distinct means They are completely separate, they do not have any relation with each other, or there cannot be any difference between them which is in terms of real integers. Now the roots are unequal and differing by an integer, and differing by an integer, differing by an integer, making coefficient of y, making coefficient of y, okay. So that is an, a0, a2, a3, etc. coefficients indeterminate, indeterminate. So this is second possibility. Third possibility in this step number 5 is roots are unequal, and differing by an integer, okay. These are notes today, we are calling, or we are writing here integer, and making coefficients finite. This is third possibility, making coefficients finite. This is the third possibility. And fourth possibility that the roots are equal. So first is they are not equal, they are completely distinct and they do not differ by real integers, first possibility. Second is possibility is the roots are unequal, that means they are not same and they differ by an integer, making coefficient y indeterminate sometimes. And third possibility is that root are unequal and differing by an integer and making coefficients finite sometimes. And lastly, the roots are equal. So these are the several possibilities as we have shown, that is to be inferred from the indicial equation. So whatever indicial equation we have obtained upper, that indicial equation tells me these are the possibilities, and based upon these possibilities our solutions may be only one power series, two power series, then combination of power series, etc. These things can be seen further when we go for actual problems. So that is what step 5. Now step 6. After step 5, step 6. Now remaining part. So out of in this equation number 3, we have taken care of this. So this first term, an times n plus k into n plus k minus 1, this is equated to 0. We got the coefficient which is called as coefficient of lowest power of x, and that is called as the initial equation. Now remaining powers of x is the intermediate power x raised to n plus k minus 1, and this is the highest power en times x raised to n plus k. Now there is something, these two coefficients also give you something very interesting, and that is called as the that equation is called as the recurrence relation. So we have to write something about this. So equating the coefficients of general powers such as x raised to n plus k minus 1, x raised to n plus k, etc. General powers to 0. Equating the coefficient of general powers x raised to n plus k, x raised to n plus k minus 1, etc. to 0. The equation so called obtained is called recurrence relation. I am sure you might not have come across these terms earlier. किंवा पूर्वी ह्या terms कधी वाचले नसतील किंवा अभ्यास नसतील, पण now we are learning method. Once we understood this method, then we are going to apply this for different problems, and in that case we will understand the importance of this recurrence relations because it connects the coefficients. It connects the coefficients. These coefficients are a0, an plus 2, or an plus 1, etc. Several different types of coefficients are there. An and this is an plus 1, yeah, an and an plus 2, and an plus 1. So if I am having this to be even, this will be odd. If this is even, this will be again even. So all odd, even and odd coefficients are connected with each other. That is called as the recurrence relation. That is what step, I think, 5, 6, and one more thing. I think we have this second step. This was step first. This is step second. Yeah, correct. Incorrect. This is step second. This is the third one. This is the fourth. Then this is this. Sorry, something wrong again. So this is step 1. This is step 2. Step 3. Step 4. Okay, we have not written step 4. There we have missed. So this is not correct here. This is step 3 is correct here. This is step 4. Then this is step 5 we have written earlier. This is your step 5, and now gets for step 6. Yeah, Roman numbers I am writing. Step 6. If the recurrence relation connects an plus 2 and an, connects an plus 2 and an, okay, n and n plus 2, even and odd, sorry, one and then next even for that, okay, an. Then if a0 is known, then a2 can be calculated, a2 can be determined. If a2 is known, then a4 can be determined, and likewise can be determined, and so on. All even coefficients can be determined. All even coefficients can be determined. That is, if the recurrence relation between an plus 2 and an is known, or if the recurrence relation is defined, and if a0 is known, the first constant a0 is known, then all even coefficients also can be calculated, as well as if an and an plus 1 recurrence relation is known, okay, and if a0 is also known, then all odd coefficients can be determined. And in the power series, a0 is known, so a1 can be calculated, a3 can be calculated, a5, a7, etc. All odd coefficients can be calculated. Therefore, as well as the second recurrence relation or the first recurrence relation which we have between an plus 2 and an, if a0 is known, so I can calculate a0 is known, a2, a4, a6, a8, etc. all even coefficients can be calculated, and using this odd and even coefficient in my power series, I can get a power series which is going to be the solution of the given differential equation. So this is what step number 6. Now step number 7. Step 7. After getting these coefficients, that is what I am just now talked about. After getting these coefficients, the solution is obtained by substituting these values in equation 2, that is our equation y is equal to summation over n equal to 0 to infinity an times x raised to n plus k, okay, and a0 is not equal to 0. So substituting in this equation, we will get the after getting this coefficient, the solution is obtained by substituting their values, these values in equation number 2, that is y is equal to summation over n equal to 0 to infinity an times x raised to n plus k. Okay, and here important statement we have tried for the existence of two solutions. Now whether this particular equation has one solution, two solutions, whatever number of possible solutions, that depends upon the following thing: the existence of two solutions and their linear dependence. Two solutions and their linear dependence, independence, not dependence, linear independence depends upon step 4. So step 4 will decide whether I get two independent solutions or two dependent solution or only one solution. That will be decided by the step 4. Okay, that is roots of the initial equation. Roots of initial equation will decide this. Initial equations, root of the initial equations. Okay, so actual examples of that will be see somewhat later on. And the last step now, step 8. Last step, check the convergence. Check the convergence, convergence, convergence of series solution if necessary. That means in the discussion, if I am getting a series solution, but if one of the term or if that particular series is diverging itself, okay, I am getting the solution but the series solution obtained is diverging, then that is not useful. That means if it is becoming infinity, at some other point that solutions are not to be accepted. So therefore we have to carry out the convergence test at the end. Now what this test is, what this test is, how it is to be carried out, what is its importance, etc., that we will see in the next lecture. But before that, let's try to understand this is the method that is to be implied or applied while getting a power series solution of ordinary differential equation of the type y double dash plus q of x in p of x into y dash plus q of x into y is equal to 0. So at the point, we have to first check the point of expansion. Okay, so these are the steps. I'll just repeat in brief. So according to this first theory, so we have to check the point of expansion of which or for which we are going to find out this series solution. First check the point of expansion is either ordinary point, regular singular point or irregular singular point. Provided if it is an irregular singular point, then there is no use of getting this particular method, because this solution is not going to be acceptable at all. And if it is a ordinary point or regular singular point, then using this method, whatever solution we get, these solutions gives you something important or something interpretable. Otherwise, mathematically it is possible, physically there is no use of such type of equations which are solved. Use it for this ordinary irregular singular point or essential singularity. So first we have to check whether the given differential equation is having a regular singular point, ordinary point or irregular singular point. Based upon that, we can go for further solutions. So first we have to assume, according to this Frobenius series, we have to assume the solution of the differential equation is of the type, this particular equation, start equation I have written here, this, so that y is equal to summation over n equal to 0 to infinity an times x minus x0 raised to n plus k. This is called as power series. Now for simplicity or for understanding purpose, let's take x equal to 0, that x0 is of course is equal to 0. I am taking that to be a point which is now an ordinary point of the given differential equation, then this power series gets converted into this. N is equal to 0 to infinity an times x raised to n plus k. Again, a0 is not equal to 0. So these two equations. So here we start. This is what our given differential equation, y double dash plus q of x, y dash plus q of x into y is equal to 0. So check the point of expansion, whether it's a regular singular, irregular singular or ordinary point. If it is there, then that particular first theorem ensures there is at least one power series solution, maybe two power series solution, maybe power series solution, but may not be power series solution. So according to this first theorem, there can be several possibilities, and therefore we can assume the solution of the differential equation in y is of the form y is equal to summation over n equal to 0 to infinity an times x raised to n plus k. This is called as power series, and assuming this to be a solution, then differentiating with respect to ones with respect to x, that is gives you y plus y dash. Then second differential gives me y double dash. Now write all these y, y dash and y double dash in our differential equations. We will get this type of equation number 3. And here in this equation number 3, the coefficient of least power of x gives you indicial equation. That is essentially a quadratic equation in k that will be solved, and based upon that initial equation, the equations based upon this roots of this initial equation, several possibilities are there for any power series for a given differential equation. Then the remaining coefficient of the remaining powers of x, that gives me a recurrence relation. So recurrence relations are nothing but these are the relations connecting coefficients. So if an plus 2 and an is known, or if a0 is known, an and a is known, an and an plus 2 is known, we can go for calculating all other even coefficients. Similar is the case for the second part, that is all the odd coefficients also can be determined if the recurrence relation between an and an plus 1 is known, and also a0 is known. We can go for that type of relationship again. So that is possible, that gives me all coefficients. Once I get that particular coefficient, these coefficients can be put in our power series and we get a power series solution there. And once we get this type of power series solution, we have to check whether two solutions are possible, one solution is possible or not, solution is not possible. And that is what again we have to take the help of this initial equation or the roots of initial equation, that is step number 4. And once we get that, we have to get a power series solution of the given differential equation, and this solution is to be checked for the convergence and how to carry out the convergence, etc. This theoretical part we will discuss in tomorrow's lecture. So today we will stop here. Remember, no one asked you this method in examination. We are learning the method. That's what we are writing all these things. You are not needed to write anything in the examination. We are only given the problems. Again, half part of the problem, 1/4 part of problem, or the total problem sometimes asked. So once we understand this method, we can use or we can apply this method for any of the problem in physics. कुठल्याही प्रॉब्लेम साठी आपण फिजिक्स मधल्या या प्रकारची जी सहज सोल्यूशन मेथड अप्लाय करू शकतो. नाउ इट्स ऍक्च्युअल ऍप्लिकेशन पार्ट, दॅट इज व्हॉट वी आर गोइंग टू डू. सहज सोल्यूशन फॉर Legendre differential equation, Bessel differential equation, Hermite differential equation, etc. And in that case, we are going to use all 7, 8 steps. Step 1, step 2, step 3 up to step 8. All these steps are to be used, and then we get a powerful, useful power series solutions of the differential equations, which are quite useful in physics. So in mathematics also, but in physics they play a very vital role and important role. And this particular functioning or this particular methods has given a rise to the, as I said earlier, it has given rise to this vector atom model. So whatever development in quantum mechanics as well as other branches of physics was possible, that was possible because of this Frobenius series solution method. So all its impact, all its importance, all its effect, all its applications, etc., that will be see in the next few lectures. Okay, so henceforth again this will be again a completely mathematical discussion. Each and every point or term you have to write on the board, then and then it will be possible for you to understand. That means if I am just go on reading, मी जर फक्त वाचलं जसं आपण पीपीटी वर वाचतो तसं आणि सांगितलं की असं असं असतं तसं असतं, no one will understand anything. Once these things go in by our hand, आपल्या हाताने एखाद्या गोष्टी आपण लिहिल्या की बऱ्याच वेळा त्या गोष्टींमधला अर्थ आपल्याला कळायला लागतो. So here today we'll stop here. Now you have to join for the next lecture for Dr. Kolam sir.